Hey everyone, this is the first day of Unit 19 here. We're going to be taking a look at something called regression for the next few days. I'm pretty confident in Algebra 1 you learn linear regression, but if not, or if you don't remember it, we're going to go through some of the details of what regression is, and today just focus on linear, even though there are many types of regression. So this first page is really just getting through some definitions and recalling some graphs that we already know the shape of. The definition that I have for regression here is that these are going to be equations that are used to model and estimate based on a given set of bivariate data. So mostly what we've been looking at up until this point has been univariate data. We've been studying things that really only contain one variable. But now we're going to be a little bit more focused on looking at how two variables interact with one another, and is there a relationship and even a correlation between the two variables that we're studying. So, like I said, today we're going to look at linear models that are used to create some estimates here. But there are other functions that we've studied this year that might model data even better. And we'll look at those probably actually more tomorrow in the next lesson. So linear, you're going to see of the form y equals ax plus b. We know that that's the general shape of the graph. And even though I've sketched a line with a positive slope, we'll actually, of course, see examples with negative slopes. Quadratic, again, depending on the value of a, it might be opening up, it might be opening down. We've studied exponential functions of the form a times b to the x. So when you have an exponential of this form, it's going to have that horizontal asymptote at y equals 0, so keep that in mind. We've studied the inverse of exponential, which would be a logarithmic function. When we do logarithmic regression, it does use the specific function ln of x. So ln of x, as a reminder, is the natural log function. It's log base e. And then we've got power regression in there. So just check out the difference between exponential and power. Power regression, the base is x, whereas in an exponential function, the x is up in the exponent. So just kind of a difference between the two examples there. And there's even another type that we'll study later next week, and that's going to be a sinusoidal regression. Sinusoidal is going to be something that's modeled by a sine function. So if we're good with that, we're going to now talk about something called the linear correlation coefficient. When we talk about correlation, we're talking about how accurate is the linear model and how dependable are the predictions that we make based on that linear model. So there's a value that we can calculate that tells you how strongly correlated the two variables are that we're looking at in our data set. So the definition for correlation coefficient is, first of all, it's defined by the value r, not r squared. When we do linear regression on the calculator, it's going to tell us both of those values. We're just going to look at the value of r. It tells us the strength and direction of our linear model. So not only just specifically how well correlated the two variables are, but r can be positive or negative. And we're going to see that in some of the scatter plots that are drawn below. So we already actually, from the definition, I said that it's represented by the letter r, but we're going to see that come up in our practice today with linear regression. So we have some graphs over here, and these are graphs that are called scatter plots. Okay, so they're not dot plots like we saw with some of the univariate data, but these are scatter plots, and you can see kind of what it looks like if the r value is 1. Here's an r value of positive 0.6 and an r value of 0. So we're going from something that has this is the strongest positive correlation you can possibly have. It's a perfectly straight line. 0.6, yeah, I mean, the data still has kind of a positive sloped trend there, but it's certainly much more spread out than this perfect straight line. 0, there's really no relationship between the two variables if the data is spread out in this format. So that's what we were looking at there. And then you could have negative correlations as well. And what this brings us into a discussion of is that r has to exist somewhere between -1 and +1. And look at how great a straight line we have if r equals -1. That is a perfect negative correlation. And I'll tell you, in the real world, +1 and -1 won't happen. If you're looking at real life data that you're collecting, you'll never get r to be perfectly +1 or -1. There's going to be some sort of variation that's going to cause it maybe to look like this, but that's still a pretty decent r value. Okay, r being -0.8, the closer you get to the extremes of -1 and +1, those are the best correlations between the two variables. If I'm looking at a linear model to represent our data set, clearly the scatter plot here is not representative of a linear model. So in this case, the linear correlation coefficient is 0. Okay. So just a little quick bit about that. Maybe you've already remembered this from Algebra 1, but let's get right into what are the keystrokes on the calculator that we're going to need, and let's take a look at some linear regression with some data concerning your IQ and the number of hours of TV that are watched per week. And if you're thinking about these two variables, maybe you already kind of know what type of relationship that we have, that as IQ increases, what might happen to the hours of TV that are watched per week, something like that. We're going to see if there's a connection there. So it says, on a grid, construct a scatter plot where the independent variable is IQ, so independent is X. Find a linear regression equation for this data, round the slope and y-intercept to the nearest thousandth. Okay. So we're going to go ahead and I'm going to quickly type the data into two lists. List 1 is going to be the X values, the IQs. And then list 2 is going to be the Y values, which are the hours of TV watched. Okay, so go to Stat Edit. I'm going to clear out what I have in my list here. Okay, if you need an extra second or two to catch up and type your data in, you'll just hit pause, right? All right, so I'm going to do this carefully, make sure that I don't miss anything. Okay, list 1 looks good for the IQs. List 2, hours of TV. Okay. Now that we have all that set up, I'm going to go to Stat, and then I'm going to go to Calculate. And you'll see that in the Calculate menu, we have an option, choice 4, called Linear Regression. And throughout the week, we'll study other types of regressions. Like I was mentioning, some of those other models. We can have quadratic regressions. We can have natural log regressions there in choice 9, exponential regressions. So those will be all things that we study coming up. But our main focus today will just be option 4 there. Okay. So we're going to get that linear regression equation in a few moments. And then we're going to also be able to answer parts B and C. So B would be, well, using this equation, let's predict if the IQ of somebody is 120. Yeah.
Sorry, that was really weird.
Okay, we have some microwave issues. Never mind. Okay, so if somebody's IQ is 120, how many hours of TV they watch per week? And then on the other hand, if we know how many hours of TV somebody watches per week, can we predict their IQ using our linear model? So we've already done this first step here. We've entered the data into list 1 and list 2. But what I want to do is take a look at the scatter plot. So to look at the scatter plot, what you're going to hit is you're going to hit second y equals. So when you hit second y equals, you'll notice that plot 1 currently is off. Maybe it's on for you, depending on what your calculator setup looks like. But I'm going to make sure plot 1 is on. The first option that's selected here is scatter plot. If you have an older model of the calculator, you might have like 2 rows of graphs like this indicates over here. My data for my X list is L1, Y list is L2, so that's all good. You can choose, if you have a color edition, whatever color you want and whatever mark you want. But once you have all that set, I'm going to check one more thing. My Y equals right now has some crazy stuff in it. In fact, I have no idea what that means. That my daughter was playing with my calculator, so I don't know what that is. Okay. So I'm going to clear up my Y equals, and I'm going to hit zoom 9. Okay. Zoom 9 is a representation of what that data would look like in a scatter plot. Okay. So now that we have that, and you can see actually how that matches this down below, it says take a guess as to what the correlation coefficient is. So would you say this is a strong correlation, a weak correlation? You know, these data points look like they form a relatively nice straight line. You know, the only thing I would really be double checking in your guess right now is that your R value is negative, right? As X increases, Y is decreasing. So make sure you have that taken into account. And we shouldn't choose -1. It's not a perfectly straight line, but you want to make sure you choose something that's pretty close to -1 in this case. All right, so now we're up to the set where we're actually going to do that linear regression. Here's what the keystroke might look like if you wanted to do it on an older calculator. But I know a lot of you have the updated model. So if you go to Stat, Calc, like I showed you before, choice 4 for linear regression, you want to make sure your X list and Y list are set correctly, L1 and L2. We do not have a frequency list. I don't think we'll ever use that for linear regression. But the store regression equation part, I do want you to do that. So I want you to store the regression equation into Y1. A couple ways to get Y1. The way I'm going to get it is I'm going to hit vars. Okay, so this button right here that says vars. And then once you hit vars, you're going to scroll over till it says Y vars. Hit enter for function, and you'll notice the first option is Y1. It's just going to take my equation that we come up with and store it in Y1. So that if I go back to the graph, it will graph my linear model against the data. So hit calculate. Here's what I wound up getting for the line of best fit. And I think it said to round up above to maybe 3 decimal places. Is that what it said? To the nearest 1,000. Okay. So the linear regression equation, correlation coefficient, we're going to do that part in a second. But I'm going to say for part A here that we get y equals negative 0.246 x, right? So notice how they give you values for A and for B. And those are going to get plugged into those coefficients. And then we get plus 38.731. Okay, so this is going to be what's called the line of best fit for our data. We're going to see how it fits the scatter plot really nicely when I go to the graph in a moment. The R value, the linear correlation coefficient, is negative 0.8733. So if you had made a guess of that in the last step, maybe you would have guessed something that, again, wasn't exactly -1, but maybe pretty close. If you said negative 0.8 or negative 0.9, you're definitely on the right track there. So if the R value did not come up for you, you should only have to do this once, but it's very possible that you got the values for A and B, but you're not seeing R squared and you're not seeing R. So really quickly, the way we're going to fix that is you have to turn what's called your diagnostic on. To turn the diagnostic on, you're going to hit second 0. Second 0 brings you to the catalog for your calculator. You're going to scroll down till you'll see diagnostic on, or an easier way to get there is you might notice that Alpha Lock is selected right now, so that means you can like start typing in letters. The letter that corresponds with D is right here, right? See the green D? So if I hit that, it's going to jump down to the letter D in the catalog, and then if you scroll down, you want to find diagnostic on, hit enter, and then hit enter again, it says done. So for those of you that didn't have that R value pop up, if you go back in Stat Calc Choice 4, and run that linear regression again, you should wind up getting the R value to pop up. If you have any questions about that, let me know. I'm going to check my Y equals line, see if the regression equation is stored there, and it definitely is. Notice how it carries it out many more decimal places than what we wrote down on our page. But if you go back and hit Zoom 9 again, it's going to graph that line of best fit with your data. And if you're not getting this same information, it's probably because you typed something wrong into list 1 or list 2. So go back and double check. I mean, all of your screens should look pretty much identical to what I have here. Okay, so double check the data that you entered. Okay, if we're good with the calculator steps there, we're going to now predict a couple things based on the line of best fit. So it says predict how many hours of TV a student with an IQ of 120 would watch, and you could do this in a few different ways. You can go to calc value and type in 120. So if you go to second trace calculate, and option 1 is value. If you type in 120, it's going to jump right to the line of best fit right here, that linear regression model, and tell you that at 120 hours, that person might watch 9.19 hours of TV, something like that. Okay. So we'll round to the nearest hour here, and we'll say that this is 9 hours. Okay. The other way to do that, by the way, is actually go ahead and enter in 9 sorry, not 9, enter in 120 the given IQ for x in your equation. So if you do y equals negative 0.246 times 120 the IQ plus 38.731. Now, keep in mind the linear model that we have typed in went out more than 3 decimal places, so we probably won't get exactly that 9.19. But if I go to the home screen for a moment and I type that in, negative 0.246 times 120 plus 38.731, I got 9.2. So something pretty close there. All right. So given a value of x, we can predict a y value using the line of best fit, and we can even do the opposite because that's what the last part says. If a student watched 17 hours of TV a week, what would their predicted IQ be? So this is where you're going to actually set 17 for y, and you're going to solve for x. So the first thing you would do to solve this, it's pretty easy to solve, right? Subtract the 38 to the other side. 17 minus 38.731 is negative 21.731. And if you divide that by negative 0.246, you get that the IQ might be somewhere around 88. It doesn't really say where to round here, so I'll say that that's my answer, 88 to the nearest whole number. Looks like the IQs that are given at the top are all in multiples of 5. But without giving any rounding directions here, we'll say that it's an IQ of 88. Okay. All right. So hopefully we did okay with all the calculator keystrokes we were walking through there. We'll do